right. Good morning. Welcome to day 3. For some reason, my slide said day 5, but day 3 of our free response review of the different types that we have. So we've been covering 2 a day. So remember, the first day was talking about tables and graphs. So what to do with the table, what to do with the graph, the questions we can ask with those. Day 2 was on particle in motion and the optional parametric motions. So we talked about those and just refreshed on those for a second. And today is about 2 different types. So we're kind of, we've been jumping around if you can't tell by the type number here, but we're going to talk about accumulation primarily in rates. Okay, accumulation. So we have a specific formula and type of problem with that. And really miscellaneous. And there's 2 types of miscellaneous that I'm really discussing here, and that's going to be implicit differentiation type of problem and related rates. Okay, those are your 2 main ones. I don't think they're good enough to have their own day or their own type, but those kind of clump together in their own little type of problem. So we'll discuss 2 examples, or example of each of those, and a summary as before. And my goal is to keep this under 30 minutes. So let's go ahead and begin. All right, here's the first type, accumulation in rates. Okay. So this is from 2000. This is an inactive problem, so we can't use our calculator. So let's go ahead and jump into this bad boy. This says that water is pumped into an underground tank at a constant rate of 8 gallons per minute, and water leaks out of the tank at a rate of square root of t plus 1 gallons per minute between 0 and 120 minutes. And at time equals 0, initially, I have 30 gallons of water. So we've seen this before. We've seen this a lot, talking about some amount of something accumulating over time. This is an accumulation problem. And more specifically, this is a rate in, rate out problem. Okay, so we're talking about a specific rate coming in at the same time a rate is leaving as well. Okay, so here's a good problem that asks a number of different things, so we'll just make sure we're good. So part A says, how many gallons of water leak out of the tank between 0 and 3 minutes? So I'm only concerned with the amount coming out. I'm not worried about the rate in, I'm only worried about the rate out. That's what leaks. So we're only going to consider this function here, the rate at which water is leaking. Okay. So if I want to figure out the accumulation of water leaked between 0 and 3 minutes, that's simply going to be the integral 0 to 3, all right, of my rate for the water leaking. So that's a 0. And I'm just going to write it as t plus 1 to the 1/2 dt. That's all it is. That describes the amount of water that is leaked between 0 and 3 minutes. Okay. Now we can do u sub to really integrate this, but u is going to be t plus 1. It's not really going to affect anything, so we'll just do power rule here. So that'll be plus 1 power is 3/2, divide is 2/3, so we're doing 2/3 t plus 1 to the 3/2 from 0 to 3. Okay. And so if I plug 3 into that, well, if I plug 0 into that, 0 to any power is 0, and it just cancels out. So really all I need to do is plug 3 in. So this is equal to 2/3. 3 plus 1 is 4. 4 to the 3/2. Okay. And then minus 0. So this is Calc inactive, and as far as part A goes, you can leave it this way because we got the answer. It's unsimplified. That's okay because it's inactive, but I think knowing part A is going to help us later on. So I'm going to go ahead and simplify that. And I got that it was 16 over 3, and y'all might want to check my math on that because that's not what the answer key got, but I double and triple checked it, and that is 16/3. Because you take the square root of 4 is 2, 2 cubed is 8, 8 times 2 is 16 over 3. The answer key has 14 over 3. I don't know why. They have the same setup, the same math, but I think it's 16 over 3, so I'm going to stick with that. Okay, which is going to change our answers from the answer key, but I don't think that's an official answer key. If I don't know. I don't know why they have it that way. Anyway, so not too bad. So let's talk about B. B says how many gallons of water are in the tank at time equals 3 minutes. All right. Now, we're going to go ahead and come up with our formula at part B. We're going to talk about how this works because I'm wanting to know how many gallons are in my tank at a specific time. With rate in, rate out problems, you have a specific formula that you follow to figure out how many gallons you have at any given time. Okay. I'm going to write it out on the summary page, but just remember it's pretty much the initial value plus the integral of rate in minus rate out. So we're going to write that. We're going to say the initial amount at time equals 0 is 30. Okay, plus. And then the accumulation between 0 and 3 minutes. So that's going to be 0 to where I'm ending up at 3. Okay. And of my rate in, so my rate in is just 8 because my rate is 8 gallons per minute. So it's constant. And then minus my rate out, which we came up with in the last problem, was T plus 1 to the 1/2 power dt. Okay, there you go. Nothing too terrible about that. Okay. Now, the reason I simplified part A is because whenever I'm integrating this, I know what this value is going to integrate to. That value integrates to 16/3. So I'm going to go ahead and write that out. Okay. So we got 30 plus the integral of 8 is just 8t between 0 and 3. And I already know that this value here from the previous problem is 16/3. Okay. So plug 3 in for t, 0 in for t for 8. I mean, that's just going to be 8 times 3 is 24. So this is 30 plus 24 minus 16/3. And honestly, guys, I kept it that way. I kept it as that as my final answer because it's calc inactive. The answer key has the same setup, but again, they chose to do 14/3 and then they simplified it. I don't know why they got 14/3, but yeah, I have no idea why they did that. So anyway, I'm gonna leave it like this. Yeah. All right, and then part C. Part C is like part C then says we'll write an expression for A of t, which is the total number of gallons at any time t. Well, we just created it for at time equals 3. Let's just create a generic one for any time t. C, this is the reason I like this problem so much, is because C is literally having us come up with the rate in, rate out typical formula. Okay, so the amount of water A of t at any given time t is equal to the initial amount, which is 30, plus the accumulation from 0 to whatever time we're looking at. So we're going to say 0 to some arbitrary time t, and then rate in minus rate out. So the rate in is 8 minus the rate out is the square root of t plus 1, which because we chose t as our variable here, we can't do t in the integral. Okay, so let's remember how we talked about how it's going to be t, or I'm sorry, I just said that. It's going to be x plus 1 to the 1/2 dx. Because t is my independent input, I got to have a different value that it's going to be inputting when I integrate it. So there you go. That's the general formula for any given time t. Okay, it's not too bad. And then D. Okay. So at what time t between 0 and 120 minutes is the amount of water? So we got an equation for the amount of water from part C, but I want to know when that's a maximum. So how can I find a maximum from a given equation? Take the derivative, set it equal to 0, solve for the critical points. That's how you find maxes, right? So, and that's where our justification is going to come in. So what we're going to do is we're going to figure out what A prime of t is first. Okay? And that's just the derivative of what I came up with in part C. So like the derivative of 30 goes away. the derivative of that integration is just going to, by FTC part 1, is just going to be the function in the integral with t plugged in. So it's going to be 8 minus, I'm going to go ahead and say the square root of t plus 1. That's my derivative. Remember, the derivative of these are just the rate in minus the rate out. That's the derivative. That's the rate of change. And we're going to set this equal to 0 and solve for the maximum. Okay. So like I can add the square root of t plus 1 to both sides and get 8 equals square root of t plus 1. I can square both sides. And t equals 63. Okay. Let's test 63. So say I plug in like 62 or 60 or say I plug in like 3 because I can take the square root of t 3 plus 1. That's going to be a positive value. And anything greater than 63 is going to make it 8 minus a bigger number than 8 is going to be negative. So that, by the first derivative test, states that 63 is a max. There's your justification. All right. We tested points on a prime of t. Now, we are on a closed interval. We are on a closed interval. So I would also suggest finding the values for a of 0, a of 63, and a of 120. I don't think it's required for this problem because we only have one critical point, meaning there's only one point that it goes up to a max and then it decreases to go back down. So 63 is guaranteed to be the absolute max. The endpoints can't be the absolute max because there's no way based off of this interval for them to ever go beyond 63. But it doesn't hurt to figure out what these values are. Like a of 0 is told to be 30, and you can find these two numbers by plugging them into the equation into part C. But for sake of time, I'm not going to do that. But it ends up 63 is going to be the max value. But there's your justification for absolute maximum, is making sure to include endpoints as well as all critical points. But there you have it. Okay, so how we feel about that? That's rate in, rate out. Very common types of questions you can see on this. Okay, here's a little summary with it. Oh wait, I'm sorry. Here's the answer key first. So let's see. Like I said, it was weird. They came up with, like, you see the same exact math that I have here, but they got 14 thirds, and that's not. That should be 16 thirds. I don't know. Which makes our answer in B a little bit wrong too. But the math's all right. It's set up right, so I don't know. Here's what we came up with in C. Except they went ahead and integrated 8t, which we left it in the integral, which is completely fine. The other alternative is to actually solve for a of t by integrating the whole thing and solving for c, which we hardly ever do. I think the best course of action is to just go ahead and treat it like this first part here. Do initial value plus rate, integration of rate in minus rate out. I wouldn't try to solve for the actual equation a of t. And then lastly in D, we took the derivative like it said and set it equal to 0, and we got t equals 63. It says since a prime of t is greater than 0 between 0 and 63 and less than 0 between 63 and 120, a of t has an absolute maximum of t equals 63 by the first derivative test. Basically it's saying we only have one max. It has to be the absolute max because the endpoints have to be below it. So anyway, I would always recommend if you're given a closed interval, I would always recommend finding the values of your endpoints and your critical points just to have a little bit of clarification. But that's just me. All right, let's move on to the miscellaneous parts. Sorry. Here's the summary of the accumulations. Things to kind of keep in mind as you're trying these. Remember that with your accumulation, it's going to be some initial value plus some accumulation. Okay. Usually it's going to, like the more complicated ones, the one you usually see is going to be a rate in minus rate out. Make sure, understand the question. Like, figure out if you're given, what are you given? Sometimes you're going to be given the actual accumulation function, or you'll be given f prime, the rate, like we were in the last problem. Know how to deal with those. I guess the biggest thing of all these is to just remember the formula, um, especially like these problems right here, in and out. So the amount is equal to the initial plus, usually the initial starts at time equals 0 to t of rate in minus rate out. That's the biggest thing. Like explaining the meaning of everything. Just make sure you know how to like use it in the context of the problem. Make sure you have your units as well. I would always recommend that. That's really about it. Y'all have seen a lot of these, and I think you're gonna do fine. All right, let's move on to the next problem. Dang it. Here's problems to try if you want to really go through. You can pause this and write these down, but here's problems if you want to try on your own of rate in, rate out problems. So there you have it. And now let's go on to the next one. Okay. The next one I said is dealing with implicit differentiation. So, I mean, I've seen this problem pop up a number of times. It's pretty simple in terms of like there's no like context behind it. They're just giving you a function with both x and y. And they just want to test your knowledge of being able to do implicit differentiation. So let's go through it. Notice the function we're given is y squared equals 2 plus xy. So the reason it's going to be implicit differentiation is because we have both multiple x's and y's. You can't get y explicitly by itself, so we have to do implicit differentiation. So it says show that the derivative dy over dx is indeed y over 2y minus x. Okay. So we have to take this equation given, and our work is going to be the answer for part A, showing that it equals this. Okay. So I'm going to do A right here. And again, this is where you got to go a little bit more detailed because you want to show that process. So if I'm taking the derivative of given, all right, when I take the derivative of y, remember implicitly it's going to be dy over dx. So that's 2y dy over dx equals. Derivative of 2 goes away, but the derivative of xy is going to be product rule. So the derivative of the first, the derivative of x is just 1, leave the second the same, plus leave the first the same, and the derivative of y is dy over dx. So implicit differentiation, deriving x is the same as usual, but taking the derivative of y is implicit. It's going to be dy over dx. Okay. So now all you got to do is just solve for dy over dx. So I'm going to get all of those terms to the other side. So I'm going to say 2y dy over dx minus x dy over dx equals y. I'm going to take a GCF of dy over dx out. I'm left with 2y minus x equals y. And then finally, divide by quantity 2y minus x to get dy over dx by itself. And there you have it. We have our answer from the those ones to show. I mean, that whole process, those 3 or 4 lines there, is our answer. Okay. All right, so we know what the derivative of this implicit differentiation is. Part B says, find all points, x and y, on the curve where the line tangent to the curve has slope 1/2. So I'm trying to find all x and y where the slope is equal to 1/2, or the derivative, or dy over dx is equal to 1/2. So I'm going to take the answer from A, which is y over 2y minus x. I'm going to set it equal to 1/2. I'm going to solve for those points. So in order to do this, I guess the best course of action is probably cross multiply, try to get rid of the fractions. So it's going to be 2y equals 2y minus x. Okay. And if you notice, that worked out pretty well for us because the 2 y's cancel. So I get negative x equals 0, or just x equals 0. So it says, okay, all the points where we have a slope of 1/2. Well, those points have to happen whenever x is equal to 0. Now to figure out the corresponding y values, I can just take this term and plug it back into my original function and solve for y, right? So I can say that like y squared equals 2 plus 0y. And solving for that, we get y squared equals 2, or y equals plus or minus the square root of 2. So it looks like there's 2 points whenever we have a horizontal tangent of 1/2. That's going to be at 0 comma square root of 2 and 0 comma negative square root of 2. There you go. And you can test those points if you really want to. You can plug them into your answer in A and see if you indeed get 1/2, but you do. All right, so that was B. Let's move on to C. So C says, show that there are no points where the line tangent is horizontal. Okay, when is a derivative have a horizontal tangent? Whenever the derivative is equal to 0. So we're going to do the same thing we did in B, but we're actually going to set it equal to 0 this time. So that's y over, this is C again, that's y over 2y minus x equals 0. And when is this the only time, or when is the only time that this can be true? Well, it's when the top equals 0 or when y equals 0. So we have a horizontal tangent whenever y is equal to 0. But can that happen? Well, what happens if I plug y equals 0 back into my original function? That's 0 squared equals 2 plus x times 0. And that goes to 0, that's 0, so we're saying 0 equals 2? No, that's not the case at all. So therefore, that was a 0 by the way. Therefore, yeah, there is no horizontal tangent. So that's a good enough conclusion for me that 0 cannot equal 2. Right. And then lastly, we're going to do D. We'll be done. I'm making really good time. All right, D says let x and y be functions of time t that are related by the equation y squared equals 2 plus xy. At time equals 5, the value of y is 3 and dy over dt is 6. And find the value of dx over dt at time equals 5. Whew. Okay, so now I'm changing up the instructions here. I'm saying in part D, no longer is it implicit towards y or x, it's implicit towards t. These are now functions of t and no longer x. So that means that if I were to take the derivative of the function from the beginning, it's no longer going to be dy over dx. It's always going to be either dy over dt or dx over dt. So we're going to start fresh. We're going to take the derivative of this with respect to t. So the first part is 2y dy over dt is equal to, derivative of 2 is still 0, but if I do the product rule with xy, the derivative of the first is now dx over dt, keep the first the same, or the second the same, plus keep the first the same, and the derivative of y is now dy over dt. So no longer over dx. Okay? And now all it wants me to do is figure out dx over dt at time equals 5, and it gives me all the other values, which isn't too terrible. So let's see, it's going to be 2 times y at this point, it says is 3, so I'm going to say times 3. dy over dt, it says is 6. dx over dt is what I'm solving for, so I'll just leave that dx over dt. Y again was 6, plus x, which I don't know yet, I'm just going to leave that blank, and then dy over dt is 6. No. Oh, it is 6. Y was equal to 3. I misspoke right here, I'm sorry. Okay, cool. Well, I got to figure out what, okay, so I got to find dx over dt. I got to find this value, but I need to know what x is first. Well, how can I find x knowing what y is? Plug it back in and solve, right? I can say that y was 3. I keep putting 6 for some reason. I can say that 3 squared equals 2 plus x times 3. And I can actually solve for x, right? Doing that, we got, let's see, 9 equals 2 plus 3x, or x equals 7/3. So I can plug 7/3 into the equation I came up with up here. And now I got enough information I can solve. Okay, so 2 times 3 times 6, that's going to be 36 equals 3 dx over dt, and then plus 7/3 times 6, isn't that just, I think that's 14. Okay. And then all I have to do is subtract 14 and divide by 3, which would be 22/3 actually. There you have it. That's the answer. So I like this problem because it refreshed us on how to do implicit differentiation. It refreshed us on doing related rates as well in part D, horizontal tangents, all that good stuff. So this is a great problem to practice all that. Here's the answers that we came up with. So remember, this whole process was our work, that we did the implicit differentiation and solved for y prime. We came up with the answer for B. We did that work. Our explanation here says the curve has no horizontal tangent. Since this is true, we did show that, so we're good. And then we got 22/3 for the last one, so we're good there. All right. So there's that, and here's our little summary of it. Remember, we talked about the implicit for this topic and related rates. I have parameter problems right here. You can cross that out. It's just saying that, well, you don't got to erase that. It's not the parameter like from Unit 9 that we were talking about. Parameter is in like for related rates, our parameter is technically t. That's all I'm trying to say. Okay. But where's my slide? But yeah, so you can kind of read through this yourself here. Just what students need to know how to do. Know how to do implicit relationships. Find the first derivative using all of our product rules, quotient rules, chain rules. Know how to find the second derivative. Okay, and remember that's substituting the first derivative into the second derivative and then simplifying it. Know how to evaluate the first and second derivative by substituting both coordinate points in, which we kind of did in the last problem. Know horizontal and vertical tangents like we did in the last problem. And I'll be able to do tangent line relationships like we've been doing with all of our problems. With related rates, know how to differentiate again, know how to set up the related rates problem, and interpret the answer. So again, we've seen a lot of this before, but it can pop up kind of like it just did in that last problem. All right. And here you have some more problems to practice all those miscellaneous types. You can see in all the comments here, they're either related rates or implicit differentiation or unique problems with those. Okay, so you can kind of look through those if you really want to. But kind of what I've already done for you is under day 3, I have set up practice problems again. Let's go right here. And the solutions to these. So we got 3 problems that are dealing with rate in, rate out. And then I got 3 problems with implicit differentiation or like related rates, that kind of stuff, or kind of miscellaneous ones with that. Question 6 is a pretty tough one, but that's a good one. All right, well, good job, guys. Y'all are going to do great. And I'm at 29 minutes, so I beat my 30-minute mark. We are good. Hope y'all have a fantastic day.